Hello, everyone, and welcome to another episode of Containers from the Couch. Today, we're going to be focusing on running DeepSeek on Amazon EKS. I'm Cy Venom, I'm your host for the day, and I'm joined by Lucas and Tiago. This week, all we've been able to see is so much buzz around DeepSeek being an open source model with really just amazing performance, ability to handle extremely complicated tasks, leverages new ways of thinking, chain of thought reasoning, and the way that the models are built are very interesting. We're going to dive into all of this and more today and show you how DeepSeek runs on Amazon EKS. Of course, if you want to deploy it on your own infrastructure, that's fine as well. But we strongly believe a lot of folks will be looking at cloud compute to fully leverage the largest DeepSeek models that are out there today that are over almost half a terabyte large, right? So Tiago, let's start with you. You have this up and running on EKS already, right?
Yes, let's see how it works. Let's start with a mathematical question, maybe. Can you solve this for me? Let's do a simple equation here, but let's see if it explains that you have to do divisions and multiplications first. And while it's loading here, it might take a few seconds to finish, but we can also see the logs of the container being hosted as well, that the request is being processed and how many tokens per second are being handled right now with these requests, so that we can see that it's really running and everything is working fine.
So we're looking at just an interface that's sitting in front of the model that's running in Kubernetes, right?
Yeah. Just a user-friendly way to show it, yes. And you can see here, it says that we have to first define the order of the operations, that you should first handle multiplications and divisions, and then afterwards additions or subtractions. So it shows the equation here to us, says that you first have to do the multiplication and division, and then afterwards you can add it. So it's easier for you to understand what the LLM did under the hood here to resolve the equation. And I think that's also a nice way to learn.
You know what this reminds me of is that really popular challenge with some of these large language models when you asked it the question, how many R's are in the word strawberry? And even the most advanced models weren't able to solve this. And the way they started to be able to solve this problem is by mimicking human reasoning, right? Following chain of thought reasoning. And we see that here in this model specifically. It breaks it into steps. It says, okay, first I'm gonna, figure out the multiplication and division, and then we'll do addition and subtraction. That's a very math-oriented question, but what we see here is that it's applying that type of logic to any question that you pass it, right?
And one thing that's interesting is that it does that reasoning before actually generating a solution. So depending on the type of question that you send to the model, that reasoning could take longer because the amount of steps that it needs to take is more to figure out the actual solution. So this is exactly how we think when we are developing code. We know the problem that we need to solve, but we need to break down those problems in fewer steps and iterate on top of those fewer steps to get into a solution. So I think this is a little bit of what the model is doing, why it's so good.
Yeah, makes sense. And by the way, so while we're waiting for this to respond, I'm sure people are thinking, why is this thing so slow? Tiago, what's going on here?
So we are running here in a machine with a single GPU. That's something that's important to notice. But under the hood, what it's doing is generating the response. And as you can see here in the logs, it's generating 16 tokens per second. And now it answered here this strawberry question as well. So let's see what the answer
Look is. The amount of reasoning that the model needed to do to achieve how many R's are in strawberry word. That's exactly what I just said.
No, that's an R, not an R. So it checks all the letters here to see if it's an R or not. And then
I just got to point out the way that it's talking and the way it's responding, it feels so human. It feels so anthropomorphic. It's what's really cool about this, and we'll dive into this in a few minutes, is the way this model is trained is so central to the answers it's giving you that even for a simple question like this, it's going to give you an answer, but before it spits it out, it's going to go back and double check itself and make sure that it's giving you the right answer. Yes, this is a fairly straightforward question, but if you apply more complicated questions to it that require high-level thinking and abstraction and a series of steps, this model can handle it. And here's what's cool, as opposed to kind of traditional operator workflows with LLMs, which require multiple LLM invocations, it's doing it all with the same invocation, which I think is really cool.
Exactly. So if you get that in the past, how we would do that, we would basically get a response from a model, parse that stuff, and then send back to the model. And it would be up to us to do that interaction to validate if the response is right or not. So the train of thought that it does, it's pretty impressive.
Okay, so Thiago, let's take it back to a word you used a second ago, distillation. What exactly does that mean?
Yes, sure. Before we explain why or how it works, let's first just cover why we do this. And the idea at the end is to have a smaller model that uses less hardware to be run and also can have faster responses, because at the end it's a less complex with less parameters. So the process to distill a model, it's basically, you can think on this like having a teacher model and a student model. The teacher model is the model that has like the most parameters, that is the DeepSeek-R1 model here in this case. There are some limitations. The model will only learn what the teacher can teach, so it won't learn anything new, but it still will have like a good performance, a comparable performance with a lower requirement of hardware.
And compute efficiency is critical here, right? Like it's a huge problem for, these AI companies as a whole, but it's also one of the reasons why there's so much public attention on DeepSeek right now, because they were able to build and train this model with limited resources, without a massive budget, and they're performing at a level of, some of the models that took a lot more resources to create. And so there's actually two phases of this we need to consider. What we're showing today is not necessarily building and training the model itself, but serving it for inference use cases. So someone out there has already trained the model. Now we're leveraging it. And for us to be able to leverage it on varying levels of hardware, we need to distill it down, right? So the largest model, the one that everyone's talking about, is the 671 billion parameter model, which is a little bit over 400 gigabytes large. And just as a rule of thumb for folks out there, to measure the amount of GPU capacity you need to run one of these models, you generally multiply the size of the model by 1.2. So the R1 model, the largest one, is a bit over 400 gigs. And so someone out there did the math. This is equivalent to about 16 NVIDIA RTX 3090s to run their largest model. It's huge, it's massive. And so basically what you're explaining is that this distillation process makes it so that the value benefit of DeepSeek can be leveraged by even some of the smallest models. Basically what we're showing is that we can run this model on NVIDIA GPUs or, the AWS Neuron-based instances, Inferentia, Trainium. And while we didn't do extensive performance benchmarking, we'll share the repo with you, so you can go through this yourself at home and see exactly how to deploy these models. Before we get into that, I spent some time earlier going through the DeepSeek-R1 paper that they released, and I think there's some really interesting bits related to their chain of thought reasoning that I wanted to share with the group here. So DeepSeek-R1 is the model that was trained from another DeepSeek model called DeepSeek-R10. It's just layers on layers. There's actually one other model below that one as well, the base model. And for folks that might not know, when these models are being trained, when they start with these base models and you ask it a question, it gives you a one-word response. If you ask it what's the capital of Texas, it'll just say Austin. Of course, we know that if we go to our favorite LLM and we ask it a question, it gives it to us in a more human-readable way. What DeepSeek did that was a little bit different in creating their model, and you can kind of see it in this chart here, is they started with reinforcement learning. And what it realized on its own was that in the beginning, the average length per response was actually really short. And purely with reinforcement learning, it was able to realize that the response length that's longer tends to be the right answer. And how does it know it's the right answer? Well, it's using reinforcement learning without supervision, right? Which is called SFT, supervised fine tuning. And so this kind of flipped the approach that DeepSeek took for training their model, as opposed to traditional models the way they're trained, and it instilled this chain of thought reasoning into the model itself. Okay, a couple more slides I just want to show, just directly from that paper. What they realized is that as part of that flow, they saw some emergent behavior, and behaviors such as reflection. And we saw this in the example that Tiago went through of it second guessing itself and looking at its behaviors and seeing that it's following this kind of chain of thought, like human-like reasoning. And the last example that was in their paper I want to show here is in the response for this, fairly straightforward mathematical question, it actually paused and it said, wait, there's an aha moment I can flag here, which is so cool. And they say that it's not only an aha moment for DeepSeek, but for us looking at DeepSeek, going through this reasoning, it's so cool to see. And the distillation process and everything else we talked about with DeepSeek allows us to share this value with all of the other models that are built out there as well.
For those folks who are not familiar with reinforcement learning, it's basically how you train your dog. So your dog is there with you, and then you want to teach your dog to sit. And then if it does in the right way, so when you say sit, your dog actually sits, you give them a reward. So a snack or something like that. So it knows that if it keeps doing that behavior, it will get more reward. So that is a basic definition of reinforcement learning. I was able to get my wife to understand what reinforcement learning is by using that analogy with our dog. So just give a 50 cents here on reinforcement learning.
Lucas, I was worried where you were going with that. That's okay for the dog. Okay, that's for the dog. That's much better. Okay. Awesome, guys. So now that we understand a little bit about DeepSeek, the way it was built, we saw it running on Kubernetes. I think maybe an elephant in the room here. Why Kubernetes? Like, why leverage Kubernetes in the first place to run this model?
I think I can explain that a little bit, and then I would like to hear Tiago's point as well. But I think is one of the best platforms that we have today is Kubernetes, because it basically created the interface between the operations team and the development itself. So let's say that you are not using Kubernetes to run this demonstration. You will need to define the EC2 instance or the virtual machine, install the drivers, then run the model, then make sure that the model is running. So we don't have a good way to control maybe additional replicas, or maybe use something to automate a lot of that process. Maybe you don't have a way to scale. You could simply set up a container in a big EC2 instance, but how you make sure that this container is running? How can you make sure that you are defining the right amount of resources so you can actually get the right instance to reduce your overall cost? And moreover, since a lot of people are building on top of Kubernetes, a lot of that expertise is already there. So I think this is one of the main reasons why people pick Kubernetes instead of any other additional tooling, because it has those controllers and things in place that makes it easier to deploy on top. And on top of that, one of the main challenges, I would say not problem, challenges that I hear from my customers and for people who I talk to is drivers. So setting up those drivers for the CUDA libraries or the neural drivers for the inferential or training instances, that can be a burden if you don't have a team that understands Kubernetes. So if you're not using auto mode, for example, then you would need to set up the node yourself. Even if you're using Carpenter, you would need an additional component to install the drivers. So this is another thing that I think is a benefit or running with auto mode, and also because we can adjust the node sizes according to the workload.
Absolutely. And so, for our viewers watching, we understand that a lot of you might not be, operations experts or IT architects that understand how all of the underlying components work. You might be data scientists. You might be, focused on just getting the model up and running. Of course, the hardest approach is going to be buy a bunch of compute, set up a server farm, and run the model. But unfortunately, if you're building that from scratch, I guarantee you we're going to be on to the next big model by the time you're done setting that up. So the next step can be deploying on cloud compute. But of course, you could start with the base EC2 image, but like Lucas said, you have to manage dependencies and the drivers and that kind of thing, keeping your image up to date. Kubernetes adds a layer on top of that. Okay, now you have to manage Kubernetes. Amazon EKS, of course, with auto mode, manages Kubernetes for you, manages the underlying compute for you. You simply tell it, I want to deploy this model. And that's exactly what we're going to show you today. Lucas and Tiago, in the span of, I'd say, the last 48 hours, pulled together, running this model on AWS, on cloud compute with Kubernetes, running on Amazon EKS auto mode. And guys, I'm really excited for you to share this sample. It's going to be in the description below, but can we see how it works?
Of course we can. I think we can start with my screen share so we can start taking a look into the repository itself. Just one disclaimer, we'll be adding additional examples and templates into that repository. So most likely by the time that you are watching this, we have changed it already a little bit on the repository, but the idea is the same. What we have here, it's basically a framework that allows you to set up an EKS cluster, then deploy an EKS cluster with auto mode and deploy DeepSeek on top of that and configuring everything that you need to deploy that. So we can go over a little bit into the repository. We have that example running Cloud Shell. So if you are new to AWS, you don't have any AWS account, you can still run the demonstration yourself. So you can run in a Cloud Shell, which is basically a virtual shell that we have in AWS that has the right permissions. And then, of course, we're using Terraform with our own EKS module that AWS has created that allows us to provision clusters with auto mode. So what I'm going to do now is actually open the Terraform code so you folks can see how simple it is to set up an EKS cluster using EKS auto mode. Here is the VPC. We're using a AWS-based model as well. And then for the EKS itself, EKS-based model as well. And as you can see here, cluster name, cluster version, and this is where you enable auto mode. So just by adding that flag here, it will enable auto mode, and now you can just launch your workloads into your cluster. For those who are not familiar with Kubernetes, in order to launch workloads in our cluster, we need a lot of additional components, scaling, metrics, and everything. So auto mode makes it easier for us to do that. And of course, some ECR repositories that we're going to use for the chatbot interface. But this is all you need to deploy an EKS cluster with auto mode already on it. And of course, go ahead.
Yeah, just to be clear, I deployed this earlier today, and Lucas, I didn't even look at that file. I just ran that one line in the README, and it worked. It was that easy.
It's a good feedback to hear. So just going over, after we have deployed the Terraform, we need to set up the node pool. So basically, auto mode is powered by Carpenter that will allow us to provision nodes using custom resources. So instead of us going there, creating auto-scaling groups and everything, we define the node definitions and parameters on what type of instances we want in that node pool. And this is a custom resource.
So that's a way for you to also ensure that only the workloads that need GPU will run on those node pools.
Yeah, definitely don't want to be using compute that has GPU optimized capacity if it's not needed. So
regular microservices on that
to run your microservice. Yeah.
Okay, perfect. So it looks like once the node pools are created, Kubernetes is essentially EKS with auto mode. It's going to provision the nodes as they're needed. So when the node pool gets created, no instances exist just yet. But when you create that deployment, that's when it'll start to provision the instances it needs, right?
Exactly. So this is what we call an application first scaling strategy. If you compare that with cluster autoscaler, is the opposite side. So we will need to set up the nodes and then everything. Now we just provision the nodes whenever we need that node. And when is it? Basically when a pod is in pending state.
Got it. So we haven't deployed the pod yet. So what does that look like?
Exactly. So to deploy the pod, let's take a look into the manifest. And Tiago actually has the demo of that for us. But let's take a look into the DeepSeek deployment manifest. Pretty simple and straightforward. We are not using any additional framework on top like Kubeflow or Ray, nothing like that. We're simply wrapping the DeepSeek model using VLLM into a deployment definition. And this is all what we are doing. So if you look, we have a namespace here. Here we have the amount of replicas, and we can touch upon that later, but we can define multiple replicas as well. And one thing that I want you folks to pay attention is this node selector and tolerations. This will do exactly what you folks told that we need to do. So this will make sure that only that the GPU pods are placed in the right node, because we have a taint for the NVIDIA GPU in the node pool, and we have a toleration for that taint in that deployment.yaml file. So we know that only those pods, a combination of tolerations and node selector, will guarantee that we schedule the pod in the right node pool, since we have multiple node pools in that environment.
Okay, and let's get into the interesting bits. What's in this deployment that's related to DeepSeek?
Let's take a look into the containers that we are using. This is where we are defining actually DeepSeek, and how we are serving that DeepSeek model is essentially by using VLLM, which is a framework who allow us to not only serve models, but also fine-tuning is a library. In this case, we are using the containers that they gave to us. So this is the container that they have in their Docker Hub that has VLLM installed on it. And the only thing that we need to do is actually do a VLLM serve and pass the model name and parameters. If we go back to the README, we're going to see that that model name and parameters are essentially the model that we are use. So DeepSeek-R1 distilled to Llama 8 billion parameters. But since it's a SAD, we could literally run any other model based on the amount of resources that we have in our cluster. Go ahead, Thiago, sorry.
No, that was exactly what I was going to say. We wanted to make it easier for you to change the model. So if you want to run any other DeepSeek model, like with another distilled model, a larger one, or even the full model, or something that is also not DeepSeek, it's just changing the model that you want to use and also the parameters.
And guys, VLLM here, it's a lot like Ollama, right? Like Ollama is a great tool for beginners to just get models up and running on their local machine, wherever, but similar use case here, right?
Right, pretty similar. You can use like the VLLM serve, like a CLI, or you could build your own serving script using the VLLM library, basically like a Python application. So yeah, it has a little bit more features than Ollama, but essentially is to make it easier to serve models in your cluster in this context right here.
And Lucas, can you show us what we're gonna replace that model name and parameters with? Like what are we actually running here?
So this is the model that we're actually running. So we are running DeepSeek AI distilled to Llama 8 billion parameters.
Okay, so we've distilled
that massive
R1 model down to an 8 billion parameter model that Llama serves. And so it still keeps the chain of thought reasoning, the benefits of R1, but distilled through Llama, smaller size, easier to run on smaller instances. So we talked a bit about how we can run it on NVIDIA GPUs or on AWS native config inferentia instances. Anything else you want to show here, Lucas, before we jump to how it works?
One last thing, and I think this is pretty important. This is how Automode or Carpenter, doesn't matter what you're using, will know which node to provision. So in this case, we're saying that we want one NVIDIA GPU accelerator, which is basically one chip on the GPU instance itself. So in this case, we can provision like G5s up into 8x large, because after 8x large, you have more accelerated chips on your instance as well. So just want to highlight this here, because this is what we would take in consideration to pick the node that we are trying to provision. Whenever we change it, we give more GPU access or something like that, that will directly impact the node that we are provisioning. So this is what Carpenter Automode takes in consideration in order to provision the nodes. Just 50 cents before we get to Thiago.
Yeah, and that makes sense, right? Because for the viewers watching that want to set this up on their own, yeah, this one instance might be fine for your testing, but if you wanted to like build commercially something on these LLMs and build something larger for a lot of users, you need to be able to dynamically handle resource requests, right? So if you have a lot of people hitting your chatbot application or whatever you built with the LLM, you want to be able to scale up quickly for that demand. So really powerful stuff just to show how Kubernetes handles the compute in response to auto scaling for you. A bit more advanced topics here related to Kata and Carpenter for custom metrics that we won't get to, but just know that the power of Kubernetes and especially Amazon EKS with Automode is being able to handle that undifferentiated heavy lifting for you. Okay, with that, Tiago, I'm sure folks want to see how this stuff actually works on both NVIDIA GPUs and Inferentia. Are we ready for it?
Let's do it.
Let's do it.
So just to explain the terminals I have here, I have opened 4. The top terminals here just have the logs of the container that Lucas just showed us, the VLLM deployment. So we can see the logs, you can see that the health check is working. And the bottom terminals you'll be using to run some requests. Instead of using the UI, this time I will just do some curl requests here directly to the API and ask to explain how to resolve our equation here again. So for you to know as well, the blue one is using NVIDIA instances. It's a G6.8x large, and the green one is an Inferentia 2 and Inst2.8x large as well. So they are similar in price. The Inferentia is a little bit cheaper, but they're very similar in price. So let me run the request here on both of them. And something interesting to take a look here in the logs itself is that it shows that is being processed, how many requests are being run. Just one here in this case on both of them. We could run multiple requests as well, but we can also see how much is the tokens per second that it has on average throughput here. In this case, it's 16, and we have the answer here already. And in this case here, it was 23 tokens per second. But don't take this as a tool for any kind of workloads, because it will depend a lot on the loads that you have in your machine. So this is just a simple test. With a single request, we can see how many tokens per second each of them processed in this case here. What we can also take a look at here, let me get this other terminal that I have authenticated. If we check, for example, the node pools here that Lucas just mentioned about. So if I get the node pools here, we can see we have the general purpose. This is one that comes with auto mode automatically. So if you want to run your applications, no GPU required, you can just use this one that comes out of the box. You don't have to create the other ones. And here you have provisioned 2 additional node pools, one for GPU and one for Neuron. If you look into those, one of them, just to have a better look, Lucas already showed them to us, but let me show the newer one so that you can have an idea as well.
It's live demo. It's live demo.
Oops. Describe. Let me get a get.
Exactly.
Let me get a get. I get to see the YAML file. Yes, it's a live demo. So here we can see we are using the instances of the family inf2. And those are the sizes that we want to capture to schedule the instances. So if you know that your model run best in a single instance, you could just type back here to a single instance. But if you're using something like Spot, for example, it's good for you to have a more type of instances that are available so that you have a bigger chance to have Spot instances available for you to be using. And another thing I wanted to show you quickly is just the DeepSeek deployment, because you should be able to see what changes. So let me just show here the pod. And I have to add a pod here at the beginning. Okay. And the namespace, so live demo. So if you look here into the manifest, we will be able to see that a few things changed here. One is the arguments that are passed. So remember that Lucas showed that we can pass these arguments in just with that set. So we changed it here. It's the same model still, but we have some additional arguments here. For example, the device we are using Neuron, and how many tests we want in parallel, the block size, and so on. But another thing that is important also to take a look at is the image. It's a different image. So we built here an image for the Neuron VLLM, and we are storing this image in a private ECR here just for this demo. But it's important for you to notice that you won't be using the same VLLM Docker image for both architectures. It's a different image, But that's all that changes, or that's almost all that changes, just some configurations and the Docker image. The model is the same. We are running the same model for both the architectures. So if you want to use inferential, you can use the same DeepSeek model as you're using on the NVIDIA instances as well.
So the new Docker image you built to run on the neuron-based, inferential instance, you can just build that image on your local machine?
You can build that in your local machine. The image, how to build the image is available on the official GitHub repo from VLLM. So you can just get the Docker file there. You just clone the repo and also build the image. We'll also be releasing this during the next days, probably tomorrow, on the GitHub repo. So how to build the image and also how to run the neural part.
Because we need to install additional accelerators like the VLLM one that it's already default has the CUDA drivers and their accelerators. We need to have the neural accelerators on the image. So we are basically using the official image by VLLM to set up neural. And the only thing that we are doing is launching a model in the same way that we are doing with GPU. Of course, the compilation time can increase a little bit. And this is something that we have seen. It takes more time to compile the model because I'm guessing it's transpiling or something like that. But for sure, we will know additional use cases and additional benchmarks on the repository that is down here in the description. So we'll be publishing new stuff there the more that we explore.
Got it. Guys, this is really awesome stuff. For our viewers at home, you can do this yourself on Amazon EKS today. Make an AWS account, follow the tutorial. Fairly straightforward to get this stuff up and running. We'll have links to how you deploy this in the description below. Lucas, Thiago, again, I want to thank you so much for pulling together the content for this demo in almost record-breaking time and coming on the show, showing folks how it's done. Anything else that you want to share before we wrap up the episode today?
I just want to say that I've read that somewhere and in some paper on the internet that I saw that someone said models just want to learn. So this is exactly what we are doing. Like we are teaching models, but at the same time, I don't know where it's going to take us. I've watched The Terminator a lot of times. So
Lucas, someone needs to go make a song. You guys have heard the song Girls Just Want to Have Fun by Cyndi Lauper. We just have to make,
of course, models just want to learn.
AI just wants to learn.
Right. I just want to say thank you, Sai, and thanks for having us here. It's a very interesting topic that we really like to explore. And I think this is just the tip of the iceberg. There are a lot of stuff that we need to explore. If you have more ideas around stuff that you want to learn here in this channel, you can comment here as well. Maybe we can do a follow-up.
Absolutely. I would love to have you guys back on the show. Thiago, Lucas, thank you again so much. And we'll catch you all next time.
Thank you.